Okay, now I will discuss a very common example from daily life which can be explained on the basis of refraction. This is, you take a glass, fill it with water and put some coin inside it, say a day. Then let us see how the image is formed if we are looking from somewhere here. We need two light rays. One angle of incidence is 0, so it will pass straight. Another one may be taken as, here the medium is changing. This is normal. So this is the angle of incidence. And here this is water. And here we have air. So this light ray is moving from denser to rarer medium. So it will move away from the normal. Let us take like this. So if we are looking from this side, somewhere here, these two light rays, they appear to come from point I and not from A. So it means this object to us appears at this position. The real depth is this much. If I take this point as B, so real depth is BA, but to us it appears at I, so depth is only BI. So it appears raised. The same is the reason why swimming pool actually doesn't appear as deep as it actually is. So the bottom appears raised. Now we can find out mathematically what is the relation between the refractive index of water, air, real depth and the apparent depth. We'll use laws of refraction. Sin I upon sin R is N2 by N1. Here this is the first medium. This angle is angle of incidence and angle of refraction is this. This is the refracted ray, this is the normal. And if extended here, so this is R. Right? This is I, this bigger angle is I. Let me take this also. C, let this point be D. ID is AC. We may need it somewhere. Okay. So sin I upon sin R is N2 by N1. This is the first medium, this is the second medium. I can even write it. N2 means air, N1 means water. So I can write it like this: sin I upon sin R, refractive index of air upon refractive index of water. Now we will make one assumption. If the angles are small, we have done it earlier too. If the angle is small, sin I can be written as tan I, and same way sin R is equal to tan R, but only for small angles. Sin 0 is 0 and tan 0 is also 0. So for very small values of angles, sin and tan, they can be taken as equal. Okay, what is tan I? Tan I is, just see from this diagram, tan I perpendicular upon base. Let me take this point as E. So it is AC upon CE. And what is tan r? Tan r I can take from this id upon ed. So id is same as ac upon ed. Okay, now take the ratio sin I upon sin r or tan I upon tan r. Tan I upon tan r. This will be AC upon CE, AC upon ED. What is ED? Now see from this, ED is same as BI. This is the depth that appears to us. And what is CE? This is BI, the real depth. So tan I upon tan I upon tan r is ED upon CE. ED is, I will write it, apparent depth, upon CE, this is real depth, and this is equal to NA upon N, or this can also be written as N water with respect to air, right? So we got an expression that real depth is refractive index of water into the apparent depth. This is always, this is more than 1. So real depth is more than the apparent depth. This is the mathematical expression. It appears to be raised. We can find out how much is that distance. It is actually at A and it appears at I. So we can find out this distance, IA. IA, the distance by which it appears to be raised. Real depth minus apparent depth. So if real is x, apparent is x upon n. So it is just x1 minus 1 by n. This is the distance by which it appears to be raised. The coin appears to be raised. Now see again quickly. An object at A, if you are looking from this side, the light ray, this one is coming straight, but this one is not coming straight. It bends actually. So if we are looking from here, the light rays are not coming like this. It is actually one light ray is coming like this and the second one is like this. So it appears, the object appears here. This is the cause that this object actually appears at this point. We call it image. And the difference we have just calculated. Okay. So this is the reason why a swimming pool always appears shallower than its actual depth. Another very interesting phenomena is let us take this as, let me take it as Earth, and suppose a person is somewhere here. So for this person, this I will say this is the horizon. So anything in this region will not be visible to this person. But let me see now what happens if I take sun at this position. See now, Earth has its atmosphere, and then beyond atmosphere there is vacuum. So when the light rays enter into the atmosphere, I'm considering just one layer. There are different layers of atmospheric air. Just considering one light ray. So the light ray, at the moment it enters into the atmosphere, it gets refracted. So it is entering from vacuum to air. Air is denser than vacuum. So it bends towards the normal. So it may go like this. Comes here. This is vacuum. This is air. So it moves towards the normal and it reaches the person. So the person sees sun at this position. So because of this, the person can see the sun even when it is actually below the horizon. And the difference in time is about 2 minutes in the morning and 2 minutes at the time of sunset. So we can say the duration of the day is increased by 4 minutes a day because of refraction. Day, I am taking the time when the sun comes at the horizon and then sets in at the horizon. But we can see it beyond that in the morning as well as in the evening. So it's all about these two phenomena. Now we shall take refraction on curved surfaces. That will be covered in the next class.